Every physical structure, from massive highway overpasses to the chassis of a commercial drone, constantly fights a quiet war against gravity and external load. The problem for engineers is that mechanical stress is almost entirely invisible. Materials degrade from the inside out, which means by the time a structure finally gives out, the failure is immediate and catastrophic. To prevent this, safety protocols rely on surface-level visual checks or external sensors strapped to the outside of an object long after it's been manufactured. But researchers recently asked a different question. What if the material itself could feel its own physical strain? Giving a physical structure a central nervous system transforms passive materials into active communicators. These objects could accurately report their own structural health and predict their breaking point long before a fracture ever reaches the surface. To build this internal nervous system, material scientists turned to 3D printing. By printing a standard thermoplastic polymer matrix and embedding a continuous carbon fiber directly down the center, they created a single, unified composite. The core mechanism of this composite relies on a physical property known as piezo resistance. When the beam bends under weight, the embedded carbon fiber physically stretches. This microscopic deformation mechanically alters the flow of electrons that are passing through the fiber, directly changing its overall electrical resistance. Because of this property, the fractional change in the fiber's electrical resistance perfectly tracks the amount of physical force pressing down on the beam. To ensure this measurement is accurate, scientists rely on specific parameter constraints. As long as variables like the material's elasticity, length, height, and width remain constant within an elastic region, the math remains reliable. By holding those physical dimensions steady, the invisible mechanical strain placed on the beam is translated directly into a measurable electrical signal. Translating that raw electrical signal into a concrete physical weight requires a mathematical bridge. Engineers use a variable called Kx, which stands for the sensitivity coefficient. This chart shows the initial calibration tests. Before embedding the material, researchers applied direct pulling force to the raw carbon fiber toe. You can see a clear linear relationship between the physical strain applied and the change in electrical resistance, providing a baseline sensitivity. But things get complicated once the fiber is actually inside the beam. The sensitivity coefficient shifts depending on exactly where the external weight presses down along that continuous line of carbon. To account for this, the researchers had to calculate specific sensitivity coefficients for multiple distinct positions across the entire structure. Mapping out these specific coefficients across the span of the beam turns an interesting electrical reaction into a precise, actionable measurement tool. To test the accuracy of their math, the team ran a physical trial. They applied targeted bending force across 7 distinct points along the 3D printed beam to see if the internal fiber could accurately report the weight. These 8 graphs plot the trial's results. Look closely at how the black data points pointer along the red trend lines at every tested position. The R-squared values consistently hit above 0.92, confirming a near-perfect real-time correlation between applied force and electrical resistance. This final chart compares the true force applied by the machine, the striped bars, against the internal calculations generated by the carbon fiber's electrical signals, the blue crosshatch bars. The maximum error rate observed was remarkably low, just 1.28%, demonstrating extraordinary precision. This precision moves self-sensing structures completely out of the theoretical phase. A composite, 3D printed structure can successfully act as its own internal load-bearing monitor. Manufacturing has transitioned to using 3D printing for reactive, smart machinery, moving past the production of inert, static geometry. For the aerospace and automotive industries, or even large-scale infrastructure, engineers can deploy parts that constantly analyze their own physical health and alert maintenance teams to wear and tear long before a failure ever happens. Ensuring structural integrity is no longer a guessing game or a matter of routine visual checks. It is an active, continuous, and highly accurate dialogue between a physical object and its environment. If you enjoyed this breakdown, please like, subscribe, and let us know what to cover next. A big thank you to today's sponsor, Synestech Systems LLC, founded by Shane Persinger, for making this deep dive possible.